Hello, my name is Tiago, and this video is just a training of my presentation to the conference IEEE 7th Global Power, Energy and Communication Conference. The title of my paper is Design and Implementation of a Kalman Filter-Based Frequency Adaptive Differentiator for a Wide Frequency Range. This is the agenda of my presentation. I will start with a short introduction. Then I'll show you the proposal and contributions of my paper. Later, I'm going to present the frequency adaptive Kalman filter, which is the core of this paper. I will move to the modeling part of my paper, and then I'll show you the frequency estimation algorithm. Later, I'm going to present the controller hardware-in-the-loop results, and finally, a few conclusions. Introduction. We know that the derivative function is commonly found in power electronics applications. We can have a computation of a derivative functions in capacitor voltage active damping of LSL filter. Very often we need to derivative a function in the virtual synchronous machine strategy and also in some algorithm of sensorless control for machines. But the differentiator process inherently amplifies high frequency noise, which usually makes this kind of solutions quite unsuitable, and a lot of people try to find different approaches to compute a derivative that do not amplify this kind of noise. So instead of using a common derivative functions, the usual authors usually propose complex algorithms to compute such a difference. And in this paper, I am presenting here a proposal in design and implementing a Kalman filter-based frequency adaptive differentiator capable of operating over a wide frequency range. In my paper, the contributions are it can compute the derivative of a sinusoidal signal with a fundamental frequency vary from 30 to 400 Hz. This is interesting because it's a really large frequency range in which you can compute accurately the derivative of the sinusoidal signal. Then you can use this as a quadrature signal generator also. And different from classical differentiators, it does not amplify noise due to the use of Kalman filtering. The combination of the Kalman filtering with the frequency adaptive algorithm, I can compute the derivatives of the input signal without amplifying noise. And this can be usually extended to input signals with harmonic content by first applying the Fourier transform, which decomposes the signal into independent sinusoidal components. As a conclusion here, I can show you that we can use this proposal to compute the derivative of the input signal even in the presence of harmonic content. It can also be used, as I said, for quadrature signal generation with a variable fundamental frequency. And all these features are attractive for digital twin applications because usually some models in our digital part have to compute the derivative of a function. This is the proposal. If you can see here the simplified block diagram, I have here the Kalman filter in black. That's the common blocks of the Kalman filter, and in red here is the proposal of this paper. I'm using here a frequency estimator algorithm to compute the frequency of the input signal, and with this result I'm going to update the matrices of the prediction of the state and the covariance error. You can see here that applying the input to the ADC converter of this microcontroller, I can compute everything, and as a result this is the derivative of this signal here. This picture already shows you the setup, the controller hardware-in-the-loop result setup, in which I'm going to run the proposed everything here in the microcontroller, and the Typhoon wheel here serve as a kind of a signal generator to input the frequency, vary the frequency, and apply all the perturbations that I need. The modeling, I won't give too much details about this, you can check later in the paper, but if you see here, we start with the input time domain signal, which is just a sinusoidal waveform. We can create another signal, which is the derivative of this first one, so the derivative of this sinusoid is just this, but we can also take the derivative in terms of omega t, which results in this frequency independent derivative function. Then we move to the discrete time domain through a sampling and holding process, resulting in this signal here, and assuming that the derivative will be correctly computed, we can construct this equation here showing the first sinusoidal waveform and its derivative, which is this one. And again, this will be free of noise because the Kalman filter will make this action for us. So knowing the time instance that we need to do for later apply the matrices in the Kalman filter algorithm, we can write these matrices here, and also later including the noise defined by n over k, we can finally have this equation. And now we can write all these equations in state space, and then we actually have the resulted matrices to be used in the Kalman filter algorithm. So notice that matrix A is frequency dependent, which we will bring from the frequency estimation algorithm. So moving to the frequency estimation algorithm, I have here all the procedures. You can also take a carefully look later in the paper, but summarizing, I have here the frequency estimation algorithm calculates the frequency of a signal by detecting zero crossing in its phase angle. Both signals from the Kalman filters I apply to this arctan function, and then it monitors the signal changes in the phase angle, computes the time period between consecutive zero crossings, and estimate the frequency as the inverse of the period. Remembering that zero crossing technique is a classical technique, but the signal must be really clean, and thanks to the Kalman filter this is achieved here in this proposal. The algorithm utilizes a circular buffer to store recent period values, smoothing the frequency estimate over time. And thanks to the Kalman filter, as I said, the signals are free of noise and the frequency is estimated precisely. Now, controller hard loop results. Allow me first to tell you how I collect the results in this setup. So the proposed of this Kalman filter with adaptive frequency estimation algorithm is tested in this microcontroller, the 28335, which is a really classical microcontroller in power electronics applications. The input signal was generated in the real-time simulator Typhoon Hill 402, which is really nice because I can change the frequency, I can change amplitude, I can change phase, I can include harmonics, which is really attractive for this kind of test. Then an interface board is used to connect these devices, and the hardware in the loop generates the sinusoidal signal, as I said, allowing me to change the fundamental frequency and inclusion of noise. Such a signal is applied to an analog output to the 402, which in turn passes through the interface board with offset adjustment, and it enters in the analog input of the microcontroller. And then to visualize internal variables of the microcontroller, I'm using here a digital to analog converter, this one, which is a 12-bit converter, so I can measure any variable within the microcontroller in the oscilloscope. That's the reason I'm showing you here results collected in the oscilloscope. So this is the classical result with the proposal. I'm changing the frequency here from 30 to 400 Hz, which is a step really hard to this, which is the worst case scenario because we could change this linearly or even in under steps, but this shows the worst case situation. And I can see here that initially both signals are sinusoidal, which means it's computing the derivative of the input signal with the same amplitude, same frequency, which is as expected. And later the signal is also in 90 phase shift here related to the derivative, and of course this has some distortions because the sampling frequency is kept constant at 10 kilohertz. Then at least I see here that the values of the input signal are properly being computed as a derivative function, noticing that the amplitude is kept unchanged. Another result here is when the input signal has noise, you can see that the derivative is properly computed and not amplifying this noise. So this is a common scenario in which you have a situation like a capacitor voltage polluted with noise and you need to compute its derivative function. We can see here that the result is quite clean. And also when you make a change in the amplitude, we can see that the independence of this amplitude is preserved, because even before and after the step both signals are being computed correctly and the amplitude is also unchanged. If you make a short comparison with other differentiators, you can take a look later in the paper details of what I use here to compare. But in the first case, when the frequency jumps here from 60 to 400 Hz, we see that even though they are 90-degree phase shifted, the amplitude is not preserved. And this is quite complicated to compensate, because when the jump is from 60 to 30, we see that here the amplitude is also modified. So it's not easy to compensate amplitude in these cases of common differentiators. And when you have noise, the situation is much worse, because the input signal has the same noise I tested previously, and you see here a classical differentiator with really high noise amplification. This differentiator is based on the central difference, which is a classical one and really used in power electronics applications. So, a few conclusions. This paper presented the Kalman filter-based frequency adaptive differentiator capable of accurately computing the derivative of sinusoidal signals over a wide frequency range. By obtaining a state space model and an adaptive frequency estimation algorithm, the proposed differentiator dynamically readjusts to variations in the input signal's frequency, ensuring precise differentiation without amplifying noise. The implementation of this proposal was based on this microcontroller, and the validation through hardware-in-the-loop results demonstrated the effectiveness of the approach in real-time applications. Compared to the traditional differentiators, the proposed method shows significant advantages, including noise immunity and adaptability to varying fundamental frequency. Future works will focus on the operation of the system with harmonic signal, as well as stability and statistical behavior of the estimation error. Thank you very much. If you have any questions, feel free to write to me. I'll be so glad to answer them. Thank you for watching.